Okay, good evening. Welcome to the Paper 2 revision session for AQA GCSE Computer Science. I can see we've currently got about 4 people watching the stream, so let's get this started. Paper 2 obviously relates to all the theory topics relating to computer systems. There's some data representation in there, networking, cyber security, and the ethical and the social legal aspects of computing, which we'll try and cover as much of as we can tonight in preparation for your exam tomorrow. Now, just so you're all aware, this video will be made available on my channel after the live stream has finished. So if you need to go back and catch up at any points that maybe you've missed, or you want to make some quick notes, or just review some of the aspects of what I've talked about tonight, you can access that on the channel and obviously look back at that at your leisure, ready for the exam. So let's get started. So paper 1 didn't really have very much binary or denary conversion, certainly had no hexadecimal really on there. So I'm going to quickly run through some of the methods of doing the quick decimal to binary, binary to decimal, and hexadecimal conversions, just to refresh your memory, ready for the possibility that it may come up on paper 2 tomorrow. Okay, so I'm going to start off with denary numbers. Obviously denary meaning our number system, decimal numbers. It's the number system that we as humans use. However, as we know, computers use binary, zeros and ones. So we need a method of converting denary numbers into binary numbers. So the easiest way to do that is to start off by writing our number line, starting from the right hand side with the number 1. Each column doubles in size, so 2, 4, 8, 16, 32, 64, 128. That will enable us to convert into an 8-bit binary number. So let's get started with the number 124. So the easiest method to calculate what our binary number would be to work out which of the numbers in our number line will add up to 124. So in this example, 64, 32, 16, 8, 4 would give us 124. And as you can see there, under each column where we have a 1, that will form our binary number. The columns that don't have a 1, or we're not using that number, we will just fill that in with a 0 to make it up to an 8-digit or an 8-bit binary number. Okay? So this is an example question. State the binary data representation of the decimal number 123. So a very similar process to what we've just done, very similar number. I would advise in the exam, make sure you're underlining keywords so that you don't get yourself mixed up as to what the question is asking you. So this is a binary number into decimal. That's the number we're converting, 123. Number line drawn in. Which numbers from the number line will add together to equal 123. So 123 is smaller than 128, so that would be a no, so that would be a 0. 123 minus 64 is our next column over. That works, we can use that, so that's a yes, that would be a 1. The remainder is 59. We subtract the next column, 32. From our 59, that works, gives us a 1, and we carry on through the calculation. 27 minus 16, yes, that works, stick a 1 in that column, it leaves us with 11. 11 minus 8, yep, that works, leaves us with 3. 3 minus 4 doesn't work, so that's a 0. 3 minus 2 works, remainder of 1. 1 minus 1 works, gives us our final 1 in our binary number, and obviously the remainder now is 0, therefore we know we finished. So our binary number is 0111111. That would be our final answer. Second way of doing it obviously is converting a binary number into decimal. So it's very, very similar to what we've just done. So we're given a binary number this time. We still write in our number line. We write the binary number in the corresponding columns below it from the right hand side. And then we add up the column headings where there's a 1. So in this instance it would be 128 plus 16 plus our 8 plus 4 plus 1, which gives us 157. Simple. Again, another exam question. State the denary representation of the binary number. So denary to binary, there's the number we're converting. Number line, write the number in below it, add up the column headings where you see a 1. So 128, 32, plus 16, plus 8, plus 2, plus 1 gives us our final answer of 187. Next, we're going to do some binary to hexadecimal. So we're given a binary number, as we can see here, and we need to convert it into hexadecimal. The first thing you do is split our binary number up into groups of 4. 4 digits, that's called a nibble. Once we have our 2 sets of 4 numbers, we write a number line above each, starting at 1, 2, 4, and 8. Second set, 1, 2, 4, and 8. We can now add up the column headings where we have a 1, so we have an 8 plus a 4, and we have a 4, a 2, and a 1. We add those up, will give us 7 and 12. But obviously in hexadecimal we use letters to represent numbers above 9. So 12 would actually be equal to C. So please remember your final answer, if it's in hexadecimal, must correspond to hex. So 7C is the final answer. Here's an exam question. Hexadecimal, binary number. There's our binary number. Same process. We move the number down under a number line. 1, 2, 4, and 8. We add the columns together where there's a 1. 8 plus 4 plus 2 gives us our 14. 14 in hexadecimal corresponds to an E, the letter E. So our final answer is E. Please note, don't be put off by the fact they've only given you a 4-digit binary number. Okay, that's not uncommon. It's not an issue. It's not a mistake. Sometimes they might do that just to trip you up. As long as you are putting the correct number line above it, 1, 2, 4, and 8, the column headings, you can still work out the hexadecimal number. Doesn't matter how many binary digits there are, as long as they're in groups of 4 from the right-hand side. Remember the right-hand side. Next, we're going to do some decimal numbers, 131 to hex. So the first process is we take our decimal number of 131 and we apply the conversion principle into binary first. That will give us an 8-digit binary number. So as you showed in the first couple of slides, find out your columns that add up to 131. Add them together. That gives us our binary number. We then split our binary number and move it down into our hexadecimal conversion. So 1, 2, 4, and 8. 1, 2, 4, and 8. We can then bring our hexadecimal number down from there. So 2 plus 1 will give us 3. We only have one column with a 1 in it, so that would be the 8. So the final answer is not 83, it's 8, 3. They're 2 separate digits that make up hexadecimal. Again, exam example. So the denary representation of the hexadecimal number 4C. So we're actually given a hex number and we have to work out the denary value of that hex number. So let's break it down. And this question, as it states here, you must show your working out to get your 2 marks. Okay. So first thing we can do is work our way backwards. So we're given 4C. Let's work out what 4 would be in a 4-digit binary number. So obviously that would be 0, 0, 1, 0. There's our 4. And then C, as we know, is equal to 12 from our hex conversions. So we move 12 up. We have an 8 plus a 4 gives us our 12. We now have an 8-bit binary number split in two. So we just move that up to the top. There is our 8-bit binary number converted from our hexadecimal number below. So the answer in denary, because this is the last part of the question, this is what it's actually asking for, okay, is the denary representation. We take our 8-bit binary number, we work out our column headings, we add them together, which equals our 76. That's our denary number converted from our hexadecimal number. The final bit on binary conversions, etc., we're going to quickly look at something called bit shifting. It's a very quick and easy method to multiply or divide a binary number by a factor of 2. So we're going to quickly look at multiplication first. So, for example, we have a binary number of 00001100, which is actually equal to 12 in denary. 8 plus 4 gives us our 12. And we want to multiply that by a factor of 2. We'll multiply it by 2. So to do that, we shift the entire binary number one space to the left. Okay. In the process of doing that, it shifts all the numbers along one space. It introduces another bit on the end, 256. Okay, but the whole number has shifted along. We end up with an empty space over here, so we have to pad that out with a 0. Okay, we pad that out with a 0, and as you can see now, the result of that bit shift doubles the number. It multiplies it by 2. We've now got a 16 added to an 8, which gives us our 24. So we very easily multiplied that number by a factor of 2. If we wanted to do that by 4, multiply it by 4, we would apply 2 shifts. Same way to the left, but we shift it 2 spaces to the left instead. So our original number is 12. We're now going to shift it 2 spaces to the left. We're going to pad it in with 2 extra zeros because we have 2 new spaces. And as you can see there, our columns with the 1 now is 32 plus a 16, which is 48. Okay, so we essentially doubled that number and then doubled it again. So we've multiplied it by 4. Similarly, for division, it just goes the other way. We just go to the right hand side instead. So if we're going to divide by 2, that same number, it's 12, we shift it to the right one space. We knock off the 0, which is now actually called an underflow, sorry, not an overflow, it's an underflow. Okay, and we pad the number out at this end with a 0. And as you can see now, the result of that is it's halved, or it's divided by 2, our original number of 12. We have a 4 plus a 2 gives us our 6. Again, divide by 4, we just shift it to the right 2 places. As you can see, our result is correct. So 3. We knock off the 2 underflows and we pad at this end with our zeros. 2 plus 1 gives us our 3. Okay? Okay, so binary, hexadecimal conversions, etc. done. As they didn't show up on paper 1, I would highly expect to see some questions on them on paper 2. It's a very fundamental part of computer science, so I'd be surprised if it is not included. So we're now going to move on to the main topic areas for paper number 2, which talks more about the theory of computing, the computer systems, input-output devices, etc., networking, that kind of stuff. Okay, so let's move on to that now. So, very basic. This is talking about input and output devices. What is an input device? What is an output device? What are they both used for? Well, an input device is, as the name suggests, is to enable us to put data into our computer. We're putting information or data via various different devices into our computer so that it can process it. Okay, so some example input devices: microphone, webcam, a mouse, a keyboard. They all enable us to input data into our computer so that it can process what we're telling it to process. And then the reverse of that clearly is an output device. We want to get some information out of our computer. That could be in printed form via a printer. It could be in audio form via speakers and headphones if you want to listen to some music. Anything that you want to see on the screen, the display, clearly has to be outputted via a monitor. It enables us as humans to see or hear or have some understanding of actually what's going on in our computer and what's being outputted. Obviously, if a monitor was turned off, the computer still runs. We just don't know it because we can't see. The output monitor, the display, is what tells us as humans the computer is actually doing something. Okay, so that's input and output device. It's very, very simple. Secondly, let's move on to something called the von Neumann architecture. So, many, many years ago, back in the early 1940s, computers were called fixed program computers. Basically, they had one purpose. Okay, so if you think about a calculator can only be used as a calculator. That's all it can do. It can't do anything other than basic calculations. Okay, however, that was very awkward, and it was quite time consuming, because if you wanted to change that computer to do something else, i.e. run a different program, you had to reconfigure the hardware, which means change all of the hardware, so that you're now putting a different program into that computer. So a very clever mathematician called John von Neumann came up with something called the von Neumann architecture. He had the idea of actually storing the program that you want to carry out alongside the data that you're going to manipulate in the same place, in the same memory of the computer. What that now meant was that you could very easily change your computer to do different things. It can now become a multi-use program. So, for example, playing a game, you can do that, and then you can switch to using a calculator. Very, very simple. The issue, however, the von Neumann architecture is that data instructions, because they're stored in memory and in the potentially in the same locations, there is a risk of data overwriting the instructions. Therefore, some very important steps need to be followed when we are writing data to and from memory to make sure that it's not overwritten. Okay, so the von Neumann architecture, here's an example diagram. So we have our input devices, as we just explained, keyboards, mice, etc. That data is inputted into our main computer system in the middle, and then we have some outputs here on the right hand side. That's displays or printing or some other kind of output from our system. In terms of the data being in the system, obviously it's stored within the memory, and the CPU, the central processing unit, is what controls that data flow. It retrieves the data from the memory and the instructions, brings it back to the CPU to carry out the instruction, and then it may have to write the data back out to memory. Now we're going to cover the way that this works briefly coming up, so I won't labour over it too much. But that's basically what the von Neumann architecture looks like if you was to draw a diagram or a model or something like that. Okay, that's what it looks like. So that takes me on to the CPU, Central Processing Unit. It has a very, very important job within a computer system. It processes all of our instructions, all of our data. They all need to be processed and carried out by the CPU. And it does that in a sequence. Okay, this sequence is called the fetch execute cycle. So the CPU will fetch instructions from the main memory where they're stored, and it may also fetch data. It brings those instructions and that data back into the CPU, okay, retrieves it back into the CPU, and then it has to decode it. What that means is it looks at what the instruction is asking to do, what the data is, it figures out what it needs to do with that instruction or with that data, and then finally it executes that instruction or executes the retrieval of more data if required. And it will go round in this sequence many times until all the processes which are part of a piece of software or a task have been carried out. So the CPU's main role, it takes our inputs, it processes it, and it produces an output. It's this key piece here that processes it, which is what this diagram here is explaining. This is the fetch, execute cycle. So it fetches, it decodes, it executes. It fetches, it decodes, it executes. It may do this billions of times a second, depending on the speed of the CPU. Okay. So the next few slides, it's an animation. It briefly shows how instructions are fetched by the CPU from memory on the right hand side, and the various buses that are used to facilitate that. So in this instance, okay, the program counter sends the location address, i.e. 1, to the MAR, the memory address register. Okay, the memory address register holds the location of the next instruction to be fetched, which in this case is location 1. That gets sent across the address bus, finds location 1, and what data is held in there. Well, in this instance, it's another instruction that says load address number 5. Okay, so that instruction has fired itself back into the CPU, and it's stored in the memory data register. Okay, so it stores that there, so we now know what we need to do next. It then increments the program counter, so it increases that by 1. It loads the instruction into cache. It keeps it temporarily just in case it needs to use it again. It sends that same instruction up to the control unit, which is where it decodes it, and it figures out what it needs to do. This is the decode part of the fetch execute cycle. It then realizes that address number 5 in memory needs to be loaded. So the memory address register holds address number 5, because that's what it needs to go to next. It then sends that across the address bus, finds address location number 5, retrieves the data. In this instance, it's the number 23. It's a value of 23. It then stores that in the memory data register, the MDR. It also puts a copy of it in the cache, but notice it doesn't delete the original instruction there. It sticks that into the cache. The value, as it's a number, it's not an instruction, is sent into the accumulator. Think of the accumulator like a mini calculator. It stores results and stores numbers. Okay. The program counter, which is currently holding instruction number 2, moves over to the memory address register. It then fires it across to memory, and it finds address location 2, which is another instruction to add that to address number 6. So it sends that across to our memory data register. It adds a copy of that into the cache memory. It increments the program counter to 3. The actual instruction, which was load address number 6, goes to the control unit, which then passes it to the memory address register, which now comes across to our memory, finds address number 6, which is the value 12, sends that across to the memory data register, puts a copy of it in the cache, and it knows it has to do an arithmetic equation, because that's what address number 2 said. Add it to the value of address number 6. So in this case, 12 and 23 are both sent to the ALU, the arithmetic logic unit. That does the mathematics and the logic of the program. It adds those together, gives us our value, the result, stores it back in the accumulator, and then program counter number 3 goes across, finds address number 3, which is store the result in address number 5. So it fires that across to the MDR. A copy is sent to the cache, and it says to store that in address number 6. So the value of the accumulator, which is currently 35, will go back to the memory data register, and it will then send it back to memory and store it in address location number 6, overwriting whatever data happened to be there previously. It also takes a copy and sticks it into the cache, just in case. It increments the program counter, because we need to carry on until we get to instruction number 4, which is an end. So we now know that we need to end that program. That is sent to the memory data register, and there's our program. It's finished. Okay. So the program counter is responsible for remembering where the next instruction is. That's what it does. It keeps a count of the instructions, starting at 1, and it goes through each instruction until it finds the last instruction, which symbolizes an end. So we now know we need to end the program. The memory address register stores the location of the address for the next instruction or data to be carried out. Okay, that sits up here. The control unit has 3 main jobs. It controls the way the data is moving around the CPU, so it basically keeps control of the fetch and execute of data. It monitors the flow of data between the CPU and the other components, such as the RAM. And it also executes the instructions provided by the program, but it also tells the arithmetic logic unit what to add together. Okay. The ALU, as I just said, the arithmetic logic unit, is responsible for doing all of the mathematical calculations, and it also deals with logic and comparisons. So an example of that would be, is A greater than B? Is B greater than or equal to A? That's a comparison. So that would be carried out by the ALU. The memory data register, that stores data and instructions that have been fetched from memory. So any data that is passed back or to the memory gets stored in the memory data register. Think of it just like a temporary location, just for the next snippet of data to carry out the next instruction. The accumulator, this is a storage location where we store the data and results from calculations. So calculations obviously are carried out in the ALU. The accumulator holds the values that will be processed in the ALU and the results of those calculations. The cache memory is a temporary location. It is used for storing instructions that are used frequently or we may need to go back to. It's a very fast, small location of memory, only useful really for holding maybe 4 or 5 different instructions, depending on the size of the instructions. The key point here is it increases the efficiency of a program. If we're constantly having to go from the CPU to the memory, that slows down a program. Introducing the cache memory as an intermediary stops that from happening. Okay, it speeds up the efficiency of our processing of our data. So this again is a quick kind of overview of how that works. So the program counter sends its next location to the memory address register, which then tells it where to physically locate that in our stick of RAM, our stick of memory. Any data that is passed back to the CPU goes back across the data bus to the memory data register, and then is stored in the accumulator, ready for any kind of calculation or logic or comparison that will be done by the ALU. So that brings me on to memory. So RAM stands for random access memory. Many computers have much more RAM in them than they do ROM, which is what we'll look at next. The image you see on the screen is a typical piece of hardware that you'd find to illustrate RAM. In laptops, it's physically it's slightly smaller, because obviously it has to fit more things into a smaller space in a laptop. They generally come in sizes of 4 gig, 8 gig, 16, 32, and as you can see there, it's in multiples of 2, very similar to our binary. ROM, however, if I just go back to RAM access, these are removable and upgradable. You can remove these, you can upgrade them, you can add more RAM to a computer system to give yourself more temporary storage and obviously speed up the performance of your computer. Which leads me on to ROM, which is read-only memory. However, this cannot be upgraded. This generally is hard soldered to the motherboard, so you can't actually remove it. And the key point here with ROM is that it is called read-only. You cannot write to it. Okay. The instructions that are held within there are generally installed at the factory, and you can't actually change the program that's on there. You can edit some of the variables and attributes of that program, but you can't actually change the program itself. Okay. So, quick things about ROM: it keeps the data even after the computer is turned off. Okay, so when you turn the power off to your machine, the data that's stored or the program that's stored in it is kept. It's used for more permanent storage, so long-term storage of data. It's known as read-only, so it can't be altered. And the data and programs held in ROM are burned onto the chips. The usual program that you would find on a ROM, on a traditional desktop computer, would be your BIOS, your basic input-output system. Okay, that is what runs when you first turn the computer on. It's what sets up the hardware, ready to boot up. Non-volatile memory. That comes to that first point. If we turn the computer off and it keeps the data, that means that memory is non-volatile. The data is not deleted when you power off the machine. A physical example here, this is a motherboard, and you can see there that chip zoomed in. You can see there it's not removable, it's hard soldered to that board. You cannot remove it without specialist tools, and therefore you can't update or change what's contained within that BIOS without specialist tools. Okay. Some examples of BIOSes there. RAM, on the other hand, is volatile, so that's the reverse. If I turn my computer off, if I turn the power off, any data that is stored in it is lost. So it is only used for storing programs and data that's needed by the computer when it's running. So as an example, if I load up Microsoft Word, I then open up a document. The document and Word, the program, the files needed for that, are loaded into RAM for the time that I'm using it. As soon as I close down Microsoft Word, it will unload that program and unload the document data from RAM and store it back on the hard disk drive. That keeps our memory running in the best performance because it can clear out any programs that aren't needed anymore, so it frees up memory. It's called random access for exactly that reason. It will randomly assign data or instructions in random locations that are available or free within the memory. The reason it does that, and the reason why it doesn't really cause much of a problem, is because the access speed of RAM is incredibly fast. Okay, so we're going to talk about secondary storage in a minute in terms of hard disks and why they store things in certain locations. But the idea here is that it doesn't matter where you store the instructions, because as long as we know where the address location is, which we will do, we can very quickly access that location within our RAM. So this is how locations work. We have a CPU, we have our RAM. The address bus, as we know, that's what finds and sends the request for the next address. So we're looking for location 1. Finds that. There's our instruction. It's some data, number 5. That instruction or that data then flows back across the data bus back to our CPU. Okay, the CPU then can obviously process that piece of information, that data, and do whatever it needs to do. Okay, so this is essentially how it works. We have numbered locations in our stick of RAM, and our data is stored in each of those locations. So if we know location 1 has the next piece of data, we can very quickly go straight to location 1. It doesn't matter if the next instruction is at location 19. As long as we know it's at 19, we can very quickly access it. Okay. So this is a very simple or a different way of displaying it, I suppose. So location number 1 has some data. Number 5, request location number 2 comes in. We get the data that's in number 2. Request location number 3, and so on. You get the idea. Okay, so let's have a quick look at an example. So the CPU, Central Processing Unit, is one of the hardware components of the computer system. Define the term hardware. So let's have a look. We could say these are some of the keywords we need to include. It is the physical, so it's not it's something we have to be able to hold and touch. So it's physical. It's the components, so you could say it's the physical electrical components, because that's essentially what's running through them in electrical voltage, and it's part of a computer system. It's the physical electrical components which are part of a computer system. That would get you your 1 mark. Okay. Again, this is the same question, but in a slightly different way. Define the following terms. Hardware. Okay. So again, physical electrical components, part of the computer system. Okay. Software, however, it's our instructions, it's our programs. Okay, it's things like Microsoft Word, Microsoft Excel. It's programs or instructions that are executed and run by the computer. The computer contains physical hardware. Okay, that's the three things linked together. So, fetch, decode, execute. This question would be asking you to describe or explain what goes on at each of these phases. So the fetch stage, it gets the next instruction or piece of data and is fetched to the CPU from the main memory. Make sure you are including where it's coming, where it's going to, and where it's coming from. It's fetching it from memory to the CPU, and it's our instructions. Okay. The decode stage is where we are interrupting or we're breaking down or understanding the instruction, i.e. identifying what it is that has to be carried out. Okay, what does this instruction that we fetched actually want us to do? And then clearly the execute stage, we're going to carry out the instructions. So data may be read from or written to the main memory as part of that instruction, but at this stage we're actually carrying out that instruction. We're doing what we are supposed to be doing, what that instruction has asked us to do. Okay. Another question here. So, used to connect different components in the CPU. Okay. Well, we know the control unit is part of the CPU. We know the ALU is part of the CPU. Ethernet is to do with networking, so that's not going to be anything to do with the CPU. And the clock, which we'll talk about shortly, that's to do with how many of the fetch execute cycles happen per second in that CPU. So by process of elimination, it has to be bus. Okay. Explain how main memory is used during the fetch execute cycle. This is a 4-mark question, so they're looking for at least 4 points here linked to main memory, because that's what it's asking. That's the key term there, main memory. So the next instruction for the current program is fetched from main memory. We're getting our instruction from main memory. Data that's being used by an instruction is fetched or can be fetched from the main menu. So we're talking about instructions and we're also talking about data. Okay, there's 2 marks. Data and instructions may be written. So that means we're not fetching anymore, we're writing stuff back to our main memory. Okay. So data or instructions may be written back to main memory during the program. Okay. And then finally, instructions or data can be overwritten during the running of a program. This may be before or after they're executed. Okay. So that's saying there that any instructions or data that we write back to RAM could be overwritten during the running of a program. Okay. So that's 4 separate points which should get you 4 marks. And then finally, increasing the amount of cache memory. So remember, that's that small amount of temporary storage. Or changing the type of cache memory can improve the performance of a CPU. But we're looking to state 2 other ways of improving the performance of a CPU. So how can we improve the speed or the performance? Okay. Well, firstly, we can increase our clock speed. The clock speed dictates how many of the fetch execute cycles are carried out per second. Okay, average CPU nowadays, if it's 3 gigahertz, we'll be doing about 3 billion instructions per second. So if we speed that clock speed up, it can carry out more instructions. And secondly, if we increase the number of cores or processors, that will allow us to carry out more processes simultaneously. So instead of doing one process, two process, three process, we're actually carrying out multiple processes at the same time. Okay. This question, most computer systems have is related to memory, have more main memory. It consists of both RAM and ROM. For each of the two statements below, shade one lozenges to indicate if the statement is true or false. ROM is volatile. Remember what volatile means. If I turn the power off, okay, am I going to lose my data or not? So they're saying that ROM is volatile. If something is volatile, we will lose the data when there's no power. And as we know, with ROM, that's false. We don't lose our data when we turn it off. Okay, ROM is non-volatile. In most desktop computers, so the average computer, there is more ROM than RAM. Remember what I said. Most computers, we have more RAM than we do ROM. Usually about 8 gig, 16 gigs of RAM. ROM, you're looking somewhere around maybe 1 or 2, maybe 4 megabytes. So a lot less. Okay. Embedded systems. So an embedded system is where you have a very simple computer that is designed to carry out a very specific task. So a washing machine, for example, is not multitask. You can't multitask. It's there to wash clothes. That is its purpose. It can't browse the web and play games. It literally washes clothes. So that includes what's called an embedded system. Okay. They normally have less main memory, so less RAM, than non-embedded, so a desktop computer. Describe two other likely differences between the main memory, the RAM, for a washing machine, and the main memory for a non-embedded, so a desktop computer. Okay, so the two likely differences. Well, firstly, programs that are stored on a washing machine will be stored in ROM. The reason for that is we don't want to change them. If we change the instruction for a washing cycle, we could knacker the washing machine. It may not carry out the wash cycle, which it's designed to do. Okay, so they don't want us to do that, so they store that program in ROM, read-only memory. And a washing machine is likely to have more ROM than RAM because it needs to store quite a few different programs, okay, different wash programs, which we can't edit. But it doesn't have to do any temporary programming of anything. There's no programs or data that will be opened up that have to be stored temporarily in RAM. So it doesn't need much RAM at all, but it does need ROM to store those programs. And there is definitely no need for secondary storage in washing machines as the programs are kept in ROM. I've gone through CPUs. We all know what a CPU is, central processing unit. It's used to do complex calculations, so the maths. The performance can be affected by the speed of the clock, that should say, the number of cores, and the cache type and size. Okay. I've already mentioned this, so I'll skip past this. CPU cores. A single core CPU is limited to doing one task at a time. It handles multiple tasks by switching between the open programs. The only way to speed up a single core processor is to increase the clock speed, so how many fetch execute cycles it carries out. We can, however, get around this problem by adding an extra core to our CPU. So we buy a CPU that's got 2 cores rather than 1. What that basically means is we can do 2 tasks at once, simultaneously. So 2 programs can be opened simultaneously and ran simultaneously. So here's an example. Core 1 could be using or processing whatever Microsoft Word needs, and Core 2 could be handling the processes and data for our web browser. Okay, so we're splitting our tasks across the cores. A 2 GHz dual core processor can process 2 tasks at once at 2 GHz, whereas a 3 GHz processor with 1 core can only do 1 task at 3 gig. Okay. So for users running one program, the single core processor is still better because it'll actually carry out that one task faster than 1 core at 2 GHz. It's actually 1 GHz faster if we're only carrying out a single task. Okay, but as soon as we introduce more tasks, that's where the dual core or the quad core processor would come into that. Okay, so storage devices. Magnetic disks. We have hard disk drives, floppy disk drives, zip disks, magnetic tape. Okay, hard disk drives are still common. Floppy disk, zip disk, magnetic tape isn't really used as much. So the only one out of those three that I would really talk about if they ask is magnetic tape. That is mainly used for backup systems. Okay, so backing up of large amounts of data, we still would do that to a magnetic tape. The main magnetic device would be a hard disk drive. We also have optical drives, CD-ROM, CD rewritable, so we can edit the contents of the disks, DVDs, and obviously Blu-rays, which I don't have on that list, but a Blu-ray drive would also be included as an optical drive. So they use disks. Lasers engrave the data onto the disk. We also have solid-state devices. These use flash chips, flash memory, rather than spinning platters, but we'll go into that in a little bit more detail in a second. You could also include flash media cards, such as SD cards, as solid-state storage devices. Micro SD cards, etc., for mobile phones would also be classed as that. So, magnetic disks, okay, they are slow comparatively to solid-state. They are cheaper, but they have much larger storage capacity. We can store a lot more data on a magnetic disk for less money. Okay. However, the downsides to that are they are slightly slower. Okay, so the access speeds are slower. They have a larger failure rate purely because they are a physical disk. Things spin and move in the magnetic disk, which of course, if anything has any kind of movement to it, the chances of it breaking down increase. And they're also quite bulky. They're quite large. If you go for a 2 terabyte hard disk drive, they're quite large, they're quite heavy, they take up quite a bit of space in your computer case. Therefore, they can be a little bit cumbersome. Solid state storage is becoming a lot more common now. They're much faster. There's no moving parts, which means they are less likely to break down, and certainly less likely to be damaged. Say, for example, if you had an SSD in a laptop and you drop the laptop, the data on the disk would be okay, whereas a magnetic disk, chances of it being corrupted are quite high. However, that does come at a price. They are much more expensive. So if you was to compare per gigabyte, the magnetic storage is a lot cheaper than an SSD. They have lower failure rates. They do have smaller storage space. So the majority of SSDs you'll find would be around about 240 gig to 500 gig. There are some larger ones. However, a magnetic disk you can get 1, 2, 4, 8 terabytes. So a lot larger storage. And then finally, optical disks. They're a little bit outdated now. Not many people tend to use them. They're cheap. They are very slow access speed. You have a very limited storage space. So a CD can only hold about 700 meg. And they are very easily damaged. They're very easy to scratch. You put it down on the surface and it will scratch very easily. So magnetic disks, they have concentric circles on the platter. So let's go back to here. The silver platter that you see there that spins. Okay, that spins round. There's circles, concentric circles. So illustrated by the red circle there. That is called a track. Each track is divided up into sectors, which is like a section of a pie or a pizza. And then there are disk heads that move backwards and forwards, very much like an LP or a record player. And it reads the data from that disk. It uses magnets. On the surface of the disk are small magnets that can either be magnetized to a positive or negative, and therefore would be a 0 or a 1 converted into binary. CDs, however, CDs use lasers. They actually burn small holes into the disk, essentially. So if there is a hole in the disk, it would be called a pit. If there is no hole, or where it goes from a hole to the fresh surface of the disk, that would be called a land. And that's how we represent our zeros and ones. The laser kind of detects those differences, and it uses a reflection technique. So the laser is reflected backwards and forwards between the surface of the disk and the laser. And obviously where it reads a variation in the surface of the disk, that's where we start to represent our binary digits. So it puts all that data together, all of those holes, and essentially creates our binary data. Flash memory, however, works slightly different. This actually is based on electric currents and electrons. So we have a layer in our flash memory, okay, and we have a series of electrons. Those electrons are flashed or forced through the barrier, and they're trapped inside that layer, okay. And depending on the sequence of trapped electrons within that barrier, that will equal our zeros and ones, okay. So if it's trapped or it's charged, it might be a 1. If it's not trapped or charged, it could be a 0, okay. I've already spoken about embedded computers, so I don't need to talk about that. Cloud storage, this is another secondary storage, saving data basically in an off-site location, such as Dropbox, Google Drive, Microsoft OneDrive. It's stored on remote servers in a data center which you access via the internet. Advantages of that: it's easy to use on mobile phones and any device really. It has high data storage capacity, so you can have unlimited accounts where you can store as much data as you want to. It's convenient to use, so users can access data from anywhere in the world with an internet connection. So you can be on the other side of the world, as long as you've got the internet, you can access your data. And again, linking back to that first point, you can do that on any device: mobile phone, laptop, desktop, you name it. Okay. Big disadvantages, however, to link to that last one, you have to have an internet connection to have access to your data. If you have no connection, you have no access. Okay. Secondly to that is the risk. There's a big security risk. They have access to your personal data. So internally, could Dropbox access your data? Okay, that's one potential risk. And then of course externally, in terms of hackers, if they can gain access to your account or to multiple people's account, they potentially have access to all of your information and all of your data. If you're storing any sensitive information, bank details, customer records, that kind of stuff, it could be potentially very damaging to your business or your organization if you were to be hacked and that data is released. And thirdly, the uploading and downloading of data could take a long time. Obviously, it's dependent on your internet connection. Okay, this third point is starting to become a little bit of a moot point, really, because most people tend to have an internet connection now, which is fiber or certainly high-speed ADSL, which means that that's not really becoming much of an issue anymore. People can upload and download data quite quickly, and of course, if you're doing it on a mobile phone device and you're on things like 4G or the upcoming 5G, then there's a potential there that actually you'll be connected at a faster rate than even your home broadband. Okay. That leads me on to software types. So there's 3 main types to consider. We have system software, such as operating systems. We also have applications, and we have utilities. There's 3 different types there to consider. So operating system or system software, it's the software that actually controls the resources of the computer. Okay, so an example of that would be Microsoft Windows or Mac OS if you're on an Apple Mac. Okay, it works to allocate memory and processor time to the processes. It also allows access to other hardware. Okay, so you as a user interact with your programs, your applications. The applications interact with the operating system. The operating system interacts with the hardware and tells it what to do. So it acts as that interface between you and the hardware. Okay, some examples there. Applications, however, these are the programs that you can install that enable you to do something, carry out a process or create something, complete a task. So things like word processors, spreadsheets, databases, presentation software is obviously Microsoft PowerPoint, computer games, any program that you install onto your computer to carry out something different other than the operating system. So these applications sit on top of the operating system. This is what you interact with as a user. Okay. And then finally, utilities. These are programs that do useful tasks. They generally carry out single or specific tasks. So, for example, file compression, where we're going to apply some compression to a file to make it smaller. You could use something like WinZip or WinRAR. That can do the file compression for you. We could do things like file conversions. So you can convert, say for example, you've got a PDF, Word document, you want to convert to a PDF. We can do that with file conversion software. Our web browsers, things like Firefox, Chrome, Internet Explorer, that enable us to browse to websites. Indexing software, which is where it searches your system and brings back data relating to your files, etc. So it speeds up access to those files. And there's many, many, many more. There's lots of little small utilities that come part of Windows, things like the clock, the calculator, screen grabber, so things like the snipping tool, disk checkers, disk defrag tools. So defragmentation doesn't really happen as much anymore with newer versions of Windows, but basically there are utilities that enable you to put all of your bits of your files into one section of a hard disk. That will speed up access time to that data. The different types of software ownership models that we can talk about, I'll very briefly go through these. So proprietary software, that's software that legally remains property of the organisation who made it. So Microsoft make obviously Windows and Office. You do not have the option to edit that software. The source code, the code behind it is closed off. You don't have the ability to edit that. And you buy license keys to enable you to use the software. Free software called freeware. Okay, it's licensed at no cost or for an optional fee. It's usually closed source, so you can't edit the actual source code, so you can't edit the program. But it is free software. You don't have to buy a software license to use it or to own it. And then finally, open source software, which is generally free. It's available to everyone, and it actually comes with the programming code or the source code open, so you can make modifications to it. You can turn that piece of software into something totally different. You can add features to it. You can help the company who made it test the software to weed out any bugs, things like that. Okay, open source software, big push for that at the moment. Things like Firefox is open source. Obviously, Linux as an operating system is open source, whereas Windows, for example, will be classed as a proprietary software. You have to pay for it with a license key. Don't need to really cover these. They won't come up in the exam. So, networking. This is another big topic. Okay. So network is a series of computers and other devices that are connected together and can share data and resources. That is a very key statement. If there is a question that says what is a network, that is the answer they are looking for. It's a series of computers. So we need at least two. Other devices could be printers and servers that are connected together to share data and resources. Okay. The third thing you could add to that would be to communicate with each other. Okay. That's one of the big uses of networks nowadays is to actually communicate and enable that collaboration and communication. The biggest example of a network in the world is the internet. It's a collection of networks from all over the world, okay, that are just physically connected, that enable access to all of the resources that we know and love and find on the internet. Advantages and disadvantages. So sharing resources, access your files from any computer in the network. Data is easy to back up, okay, because it's all stored on one machine rather than on individual machines. And of course you get the use of messaging, email and other communication tools. Some disadvantages, however, hardware for networking can be expensive, okay. If you want to join 30, 40 computers together, you're going to need servers, you're going to need switches, and they are expensive, okay. Managing a large network can be complicated. You generally need specialist trained staff and technicians who understand how these networks are connected together, what some of the pitfalls might be, and obviously how to fix problems when they go wrong. That generally costs quite a lot of money to have those staff. And then, of course, things like security problems. So if you have viruses or hacks on the network, there is the potential there that it may infect every computer on the network. Okay? If you don't have suitable antivirus software in place, there's a good chance that most computers on a network could become infected, especially if they share the same security holes which the virus has actually exploited in the first place. So if they're all running the same version of Windows and they haven't been kept up to date, then of course that virus can easily spread. Some key factors about the performance of a network. Okay, so obviously the speed, is a big thing when it comes to the network. Everyone wants to make sure the network is running at its fastest speed. So there's various things we can do with that in terms of the connectivity methods. The cost, obviously cost comes into networking a lot. If you want the best out of your network, then of course you need to be prepared to spend the money. The security of our network needs to be secure, so we need to make sure that we've got suitable methods of security in place to stop any hacks or viruses, etc., or unauthorized access. Availability, that talks about how available, so is the network up most of the time? Okay, how available is it? Okay, scalability, if we need to make the network bigger by adding more computers or more services or servers, how scalable is it? Is it easy to make that network bigger and add extra functionality to it? And then, of course, reliability comes into it. How reliable is it? How much uptime have you had? Has the network ever dropped out? Has the internet suddenly stopped working? How reliable is it? Okay, and then, of course, the topology is how that network is structured, how it's logically laid out within your organization. There's two main types of network. We've got a wired and we have a wireless. So this is talking about how these computers are actually connected into our network. Obviously, a wired would use a cable that plugs into your computer, whereas wireless would use a radio frequency to communicate with a router or a wireless access point. Okay, so there's no wires for this one, but there is for this one, and of course that comes with some advantages and disadvantages. So, wired, the benefits or the advantages: faster connection, higher bandwidth, so we can transfer more data within a certain amount of time. Okay, much greater security. Okay, think about it with wireless. You've got your data just floating through the air. Okay, wired we don't. The risks, however, generally come down to a physical thing. So cables can be hazardous, so easily tripped over. Okay, but they can also be unsightly. They can sit under your desk and look particularly unsightly. They can be trailing across the floor. Okay, this is a more common one. Not all devices can connect via a cable. Okay, if you have a new Ultrabook laptop, for example, that may not have a Ethernet port, you cannot physically connect a cable into it. Okay, and they can be expensive. As I said, the cost of switches and hubs and things like that, they're very, very expensive. Wireless devices, however, benefits: we have no wires. We don't have this unsightly and hazardous potential. Okay, it's easy to connect new devices to our network as long as you've got the wireless password, and they can be used freely within a specific range. So if we're talking about in a school, you could, for example, take some laptops out onto the field using wireless and work from outside the building. However, connection speed can be a lot slower. They're subject to interference from walls and metal within those walls and other devices, and they are less secure. Those radio waves are just floating through the air. Okay, so types of network here. We've got a LAN, stands for local area network, so it's local to us. Okay, a LAN operates on a single site, so a single building. Okay, could be an office, could be a school, could be your home. Okay, and it's usually over a small area. Okay, so a school may not seem like a small area, but in terms of geographically, it still is classed as a small area. Okay, a WAN, a wide area network, is any network that uses a third party to connect. Okay, so you could have two offices, one in Paris, one in London. Those two offices are connected via their internet connection provided by BT, for example, and it transfers that data across the internet. Okay, across the internet, and joins those two offices together. Different types of cable. We have copper cable, Cat5, Cat5e, Cat6. Okay, it's twisted pair cable. It uses copper, and it carries electrical signals through that cable. Okay, fiber optic, however, uses light. It beams a fiber optic beam of light down that cable from one end to the other. It offers extremely high bandwidth, so that means we can send a lot more data down a fiber cable than we can down a copper cable. Bandwidth, this is where we're talking about the maximum amount of data that can travel through a channel. So think about a motorway, okay? That is an idea of bandwidth. So we can transfer many more cars across a multi-lane highway compared to a dual carriageway. Okay, we still transfer cars, but a lot less. Okay, throughput is how much data we can push down a connection. So in this example there, we can see it's nearly 40 megaseconds. Okay, so that's our kind of speed of our transfer for our internet. And then finally, a PAN, personal area network. These are centered around a single user. single user. So for example, Bluetooth can be used as a radio system to connect devices. We can tether devices such as a mobile phone to a hotspot, okay? Smart watches such as the Apple Watch, okay, or wireless headphones like the set of Beats headphones. We can connect those via Bluetooth to our mobile phone, and those two devices then are connected and can share information, share data. All devices are very close to one another, so generally within a few meters, okay? The other example could be your mobile phone connected to your car stereo in a car, okay? Uses Bluetooth to do that. Star topologies looks exactly as it says. In the middle you have a central device such as a switch, and then each device comes off of that switch, so each computer is physically connected to that switch, okay? It's the most popular way of setting up a network, and you'll generally find it in a smaller network. Much larger networks tend to use different types of topologies. So the advantages: fast data transfer as there are fewer collisions. So if that computer is communicating with this printer, okay, it has a direct connection via the switch. It's not going via any other computer, and the switch handles the data. It transfers it at the right time in the right order to where it needs to go. Okay, so it reduces that data collision. And if one cable fails, the other workstations are not affected. So if this cable gets cut here, this computer will stop working, but every other single device on the network will carry on. It does require that additional hardware, such as a switch. Okay, that is one of the disadvantages. And if that central switch goes down, they all stop working. Okay, because they all connect via that switch. The second type is a bus topology. So you have a central line down the middle, and then each of your machines are connected to that central line via their own cables. And at either end, you have what's called a terminator. This is designed to reflect back those signals back along the cable so that it can get to the computer it needs to. However, it can create a lot of data collisions. If this computer is sending data at the same time as this computer, that data has to travel through that single cable. They can collide and get deleted. Okay, so therefore it would then have to send that data again. So less cables needed. That's an advantage. It's easier to install because you only have that single cable. Because you need less cables, it is cheaper. Okay, there are more collisions because you have the machines on the network and obviously only one cable for it to transfer the data across. If that main cable fails, the whole network fails. So if that cable gets cut there, that machine stops. If the cable gets cut there in the middle, they all stop. Okay. Every workstation sees all of the others. This is a big security risk. So this computer here can see this one on the network. So if you can see it, you can physically interact with it, and therefore you could cause some security issues there. And as I've already said, more collisions when you have more machines on the network. So here's another drawing. So a bit more of a specific drawing. We have a server, we have some computers and a printer. They're connected to the main bus cable that runs along the middle, and at either end you have your terminators. Protocols. We have a few different protocols to use. We have HTTP. This is used to access and receive web pages. So for example, bbc.com, that is a HTTP request. Okay, it transfers a packet from your machine to bbc.com's website server and says, can you send back all of the files that will enable me to display that website? That is handled by the HTTP protocol. Okay, HTTPS, very, very similar. The difference is it's used for secure websites. So for example, paypal.com or lloydsbank.com, they will have a HTTPS address because it secures the data. The transfer of that data is secured using an encryption method, and you will see the little yellow padlock up in the top left hand corner usually of your browser to illustrate that it's running in a secure mode. Email protocols, we have three to be concerned with. So we have SMTP, Simple Mail Transfer Protocol. It's used for sending. So SMTP, S is for sending. It sends that email between servers, and it's also used for clients to send emails to their first server along the way, and then the servers transfer it across the internet to the destination. Okay, so that's for sending. IMAP is used for receiving. Okay, receiving emails, IMAP. It downloads just the header, so just the subject line and who it's from and some very basic information. And then if you open that email, it then downloads the full message. Okay, so it only gets the initial data, and then if you're interested and you open it, it then pulls the full message down. However, it leaves a copy of that email on the server. Okay, leaves a copy on the server. The other method, however, is POP. Okay, it's used for receiving emails from servers, but it downloads the entire message, and usually it will delete it from the server. Okay, so if you are downloading all of your emails to your computer using POP, and then for whatever reason your laptop decides it's going to stop working and you need a new laptop, then obviously all of your emails that you've downloaded will be gone. You won't be able to retrieve them. Okay. However, with IMAP, because it leaves those messages on the server, you set the laptop back up, you reinstall the software, you set your email account back up, and it will pull all of those emails back down for you. Okay, so it's a backup. That's for receiving. So SMTP, sending, IMAP and POP for receiving. Okay. What do they stand for? Well, SMTP is Simple Mail Transfer Protocol. IMAP is Internet Message Access Protocol. POP is Post Office Protocol. HTTP is Hypertext Transfer Protocol. And then obviously HTTPS, Hypertext Transfer Protocol, secured. It's the S on the end. FTP, this is used for transferring files. Usually it's used for transferring files up to a web server. So if you've built a website locally on your computer, you then need to put those files somewhere on the internet on a server so that people can access them to load your website. You would use an FTP system, or the FTP file transfer protocol, to do that. Okay, you would set up your connection between you and the server, and then you start the transfer, and those files will get individually loaded up onto the server. So how do these protocols stack together, and how they related to how we generally do networking on computers? Well, we use what's called the TCP/IP stack. Okay, so we have 4 layers to this stack: the application, the transport, the network, and the data. Okay, the data link. So at the very top of that tree, the application, that is to do with your programs. The transport layer, that is to do with breaking your data down into packets. The network layer is to do with assigning your IP addresses, so it knows where it's going. And then the data link layer is to do with the physical sending, the actual hardware, the cables, the network cards, the routers, that kind of stuff. That works on the data link layer. Okay, so your computer application creates the connection, sends and routes the data, and that's the physical hardware. Okay, so that's the sending. And then when we receive, it works back up the tree. So we receive it, we figure out who it needs to go to, we recreate the packets, we put them back together, and then we can display whatever it is we're looking to display within the application. So it comes back up that stack. Okay. The network applications you're using to operate on the application layer, so things like Microsoft Outlook would use the application layer. Okay, computer games would use the application layer. And it dictates how data moves in and out of applications, and this is done through the protocol. So HTTP, HTTPS, POP, SMTP, and FTP, they would all work at the application layer. Okay. The transport layer, as I've said, it breaks the data down. So this is a picture. You can imagine it's broken it down into its individual packets. Each packet is then assigned relevant data. It's then passed on to the network layer, which then assigns the address of where it's coming from, the source address, the destination address, which is who it's going to, the packet number, so 1 of 1,000, and it applies some kind of checksum, which is like a maths equation, just to work out that the data hasn't been tampered with. Okay, and then finally it's sent out over the network card onto the internet and wings its way to the destination. I've already spoken about this with how the transport layer works, but this is talking about the transmission control protocol. So when sending data, the TCP rules include dividing the message into chunks called packets. It adds a sequence number to each packet, so we know how many there are to reassemble them, and it adds the error correction information. And then when we receive that TCP packet, it examines the packet for errors using the checksum, the error correction. It fixes any errors or re-requests packets if they're not arrived. And then if all the packets are present, it puts them back together using the sequence number and reassembles the message or the item. Okay. The UDP, however, works very similar. The only difference here is with UDP, it doesn't check whether any of the packets are corrupted or whether it's received them all. Okay. If it's only received 50 out of 100, it doesn't re-request the other 50. It just carries on. Obviously, wireless network interface cards are self-explanatory. IP addressing, every computer is given what's called an IP address. It's an individual number. Every piece of information or packet that you send is labelled with your IP address and the IP address of who it's going to, and they're sent across the internet separately via different routes and reassembled at the other end. There are many IP addresses. You won't be asked a question about this. MAC addresses is the individual number that's assigned to the interface card. So this number doesn't change. That's the key piece of information. It doesn't change. It's hard-coded into your device. Okay, and it's an identifying number so that you can send data internally on a network. The switch will use your MAC address to determine where you are on the network so that it can transfer data. Skip past those. So some exam questions. Draw a diagram showing the 4-computer network using a bus topology. Well, draw the line in for our bus. We have 4 computers because it states 4 computers. We put our terminators on the end, okay, and label them. You must label your diagrams to clearly indicate what it is you have drawn. Okay, so main bus cable, computers, computer connection, terminators at the end. Okay, this is a star network. They're connected via a switch. What network topology is shown? It's a star. State 2 advantages. Well, new computers can be easily added to the network. We just plug them into the extra port on the switch. If one device fails, the network will continue to work. So if client 3 fails and drops off, the rest will not be affected. There's improved performance. There's less data collisions. Okay, so the switch will handle the transfer of the data to make sure it gets to where it needs to go. And data is only sent to the intended device. So client 3 is sending an email to client 1. It will only go to client 1. It won't go to the server or to client 2. Okay, so there's 4 points there, and you only need 2. Okay. DNS is how we convert our web addresses, our URLs, bbc.co.uk, into an IP address. This is the address of the server that's somewhere on the internet that hosts the files for that website. Okay. We don't, as humans, don't work with numbers, we work with words. Hence why we have a system, a bit like a phone book, that translates the numbers into the words. So it's easy to remember. bbc.co.uk, easy to remember. 173.16.3.20, it's not easy to remember. Okay, there's many servers all over the world. What is a computer network? I told you that was a question. So 2 or more computer devices connected together to communicate and share resources. That is a perfect answer that will get you 2 marks. Okay, you've indicated it's computers, 2 or more connected, and you've given some reasons why we connect them. Okay. Most schools have a computer network. Some schools allow teachers to access the school network from their home computers. Give one reason why some schools would allow this and why some schools would not. A reason for it. Well, teachers can work from home, so they can access files on the school network. They can access students' work remotely, which allows marking and planning. However, there are data protection issues. Schools may not want potentially sensitive student information to be accessed outside the school. If the computer you're using is accessed by multiple people, they may be able to access the sensitive data. A PAN and a LAN, they're 2 different types of network. Describe one difference between a PAN and a LAN. Well, PANs are centered around one person. LANs cover a limited or a small geographical area. Okay, LANs cover a larger area than PANs. So there's one difference. Okay, PANs have one user. LANs will normally have more than one user. PANs will use Bluetooth, whereas LANs can use alternative protocols or connection methods like cables. Give one example of where a PAN could be used. Bluetooth wireless headphones connected to a smartphone. Any wearable computing device, such as a smartwatch, that connects to another device, such as a smartphone, wirelessly, using Bluetooth. Schools should use a wireless network instead of a wired network. Discuss the statement. Okay. Well, there's reasons for both. Okay. As long as you are picking an argument and then you are discussing some of the benefits of your argument and some of the disadvantages of the other, that will get you the marks. So schools should use wireless networks. They're higher bandwidth. They make a use of a lot of multimedia materials, PowerPoints, etc. They need high bandwidth and a reliable system so there's no delay in lessons. Okay, because it's not acceptable. There's better security on a wired network, making it more easier to control or monitor. And it allows better network performance. We have a large number of student-owned devices using the network at any one time. Okay, the performance may be impacted. Okay, using wireless networks, it allows students to make use of their own portable devices. It maintains a safe learning environment because there's no trailing cables, etc. So there's no hazards, trip hazards. It allows computer devices to be used outside the lessons, so in PE lessons you'd be on the field, for example. Limited budgets in schools, it's cheaper to use wireless than it is wired. Less cables, so less drilling, less work that needs to be carried out to install the cables. And of course many devices no longer have ports on them, so iPads, for example, don't have a network port. When two computers on a network communicate with each other, they need to use the same protocol. Define the term protocol. Well, it's a set of rules. Those rules are defined and they allow that communication. It's guaranteed. As long as we're following, these two computers are following these rules, it's guaranteed to work. Okay, so that's two key points there for protocol. One logins, so show which protocol is used to retrieve email. So retrieving email from a server. Retrieving, so we're receiving, that is an IMAP. Used to make a payment securely when purchasing goods from a website. So securely, it's HTTPS, okay. And then used to send, so SMTP for sending, okay. So onto cybersecurity. Passwords, we need to make sure we're using secure passwords between 10 and 15 characters. That is called a length check, so we're checking that the password meets those criteria. And we're using a mixture of numbers, lowercase and uppercase characters, and symbols. Okay, so things like question marks, brackets, exclamation points, things like that. Okay, they are symbols or special characters. Penetration testing, this is where you attempt to gain access to a network. Usually these are companies that are employed to come in and test the network. You have two types. You have black box, and the idea of that is to simulate an external hacking attack against your network. So the person carrying out that attack has no knowledge of your network. Okay, they are simulating an external attack by someone who is unfamiliar with the network, whereas white box penetration testing is used to simulate a malicious insider. So someone who may work for the company, may have some basic knowledge or some basic usernames and passwords, and the idea there is to see how far can they get with their hacking attempt. What can they actually get access to? Okay. So there's a few key things here when it comes to cybersecurity. Okay, so authentication, that talks about usernames and passwords. What makes good usernames? What makes good passwords? Making sure that passwords are kept secret and are changed frequently. Encryption is where we take some data and we will scramble that data so that no one can read it. You need to have the correct keys at either end to be able to read that data. A firewall, that's a physical device, usually embedded within a router, that will actually screen all of the data that goes in and out of the network. And it will look for certain types of traffic or certain types of protocols and data, and it will block that data from coming in or out of the network. Okay. Social engineering techniques, there's a few different techniques you need to know about. We have shouldering, which is where you basically stand over someone's shoulder and you watch them type their username and password in. There is also blagging, where you may try and persuade someone to help you get access to something. They may masquerade themselves as a friend or a loved one or someone you know. and they'll give you a story that basically they're looking for some help or for some money, for example. So they might give you a credit card or a bank account, get you to transfer some money. You also have phishing, which is where you're sending unsolicited emails to people, where you're asking them to do something. So, for example, go to a website and change your username and password because your account has been hacked, or type in your credit card number to update your payment details, for example. But actually, you're being taken to a website that is malicious. It looks like the correct website, but actually it's not. Okay, so the idea there is to get some personal data from you. Another type of social engineering could be something called farming, which is very similar to phishing, where the idea there is they're trying to get you to go to a website to do something. However, they actually use the DNS system, the domain name system that obviously translates IP addresses and URLs, and it will actually divert you off to a website that will look incredibly similar to the one you're expecting to go to. Okay. Once you're on that website, obviously you might key in your username and password, and then they've got your data, they've got your information. Okay, so they're the key social engineering. Social engineering is about using human beings' gullibility and personal nature to gain access to systems. Okay, it doesn't have to be technical at all. Malicious code is where we start talking about the technical aspects. So things like viruses, okay, Trojan horses. So a Trojan horse is where you may receive an email that has an attachment. That attachment looks, doesn't look suspicious in any way. But as soon as you open that attachment, it actually infects your machine with a virus. So that would be some kind of malicious code. That virus obviously could damage your system. The second thing that we could look at in terms of malicious code could be something called adware or spyware, which is more about stealing your private data. It's about spying on you, basically. They're not there to damage anything. They're not there to cause any issue with your computer. They're there to steal your data, steal your information. It might be a keylogger. So when you type your username and password into Amazon.com, for example, they've now got your username and password, okay, from that keylogger. So there's lots of different types of malicious code that can be executed on your system. The usual access route for that is via email or downloaded files, maybe that you've downloaded from a website that's maybe not particularly safe. Okay. So moving on, we can default passwords. We need to make sure that passwords obviously are strong. They cover those points I made earlier about the length and the complexity. We also have things like misconfigured access rights. So a employee at a company may be given a username and password and have access to a certain part of the network or a certain part of the server. However, if they don't need access to that, there's no reason for them to have it. Okay, so if that username and password does ever get leaked or found out, then potentially you could get access to parts of the network that are a lot more sensitive than that person actually needs access to. Okay, so that's where we're configuring our access rights incorrectly. And then finally, we have things like unpatched software or outdated software. So a piece of software that has some security holes or bugs and it hasn't been patched, so it hasn't been updated, okay? Or old versions of software. So things like Microsoft XP, for example, that's a really old version of Windows now. A lot of people still use it. However, it has a lot of problems, a lot of bugs and software glitches that Microsoft have now said that they're not going to keep up to date. So if you're still running Windows XP and you haven't got any recent updates because Microsoft don't release them, then there is a potential there for a hacker to maliciously gain access to your machine. Okay, so there's a few different things there to consider. The cybersecurity question here on screen, this is actually a 9-mark question. Okay, so list 3 different measures that can be used to maintain the security of a computer system. For each measure, so each one that you outline, so 3, you need to outline what the measure is and explain what types of threat to cybersecurity it is effective against. Okay, so this is talking about how we stop cybersecurity issues. Okay, so 9-mark question. It wants 3 different measures. Okay, so you could implement a virus checker. To outline, it scans the files to look for malicious code. Okay, It needs to be updated regularly with the latest virus definitions, so it keeps itself up to date. And it can quarantine it can quarantine viruses, delete malware, or suspicious files. And it is effectively used against malware and viruses. Okay, and give some examples of those. Okay, so the idea here is we have a piece of software that scans our files, looks for viruses, and quarantines or deletes them. The firewall, as I've said, to outline it, it analyzes or scans network traffic. It blocks traffic from suspicious hosts or computers or addresses or ports. It's very effective against hackers and the transmission of malware. Okay, so the spread of those viruses. You could use a login system or authentication or password. We could also look at things like biometric. So we're not using a physical typed in username and password, using things like iris scans from your eye or your fingerprint. That's a biometric. So the user has to enter their username and password. It can be authenticated by other methods, as I've just said. They need to match, those details need to match a database. Okay, and it's very effective against hackers. The stronger the password, the stronger the authentication, the less likely a hacker is to get into your network. And obviously things like unauthorized access relates to other employees. If they can guess your password, then there's a chance they can go on and maybe use that network or use your computer inappropriately. MAC address filtering. So as I said, each computer has its own unique MAC address which doesn't change. So you can actually set up in your router filtering against that MAC address. So we can say that each device configured via its MAC address can have access to certain things. Okay, so to connect to a network, the device must have an address within that list. If that MAC address isn't in the list, they don't get access. So that will stop unauthorized devices. So if you brought your laptop into school and its MAC address is not in the list, it can't access our network. Okay, encryption. So that's where data is stored or transmitted as ciphertext, so it's in a coded form. We've scrambled the data. Okay, only people who know the encryption method and the keys can read and decrypt the data, and it's very effective against data theft. Okay, so if they've stolen some files but they're encrypted, there is no way for them to read the data within those files. We can also do some more physical things, so the prevention of the use of external storage devices such as USB flash drives. So the ports can be disabled, so we can't actually plug USB devices in. Okay, the storage devices connected to them cannot be accessed, so we can run that through the software. So we can say that although they can physically plug them in, they don't pop up, so we can't access them. It's effective against putting malware onto a computer that has been spread by a USB device, and also the theft of data. If we have sensitive data, it stops us storing it on that USB device and then taking it off-site. Access rights. So users are associated with certain privileges that give them access to certain files and levels of files. It may stop them from actually accessing or running certain files, gives them different levels of internet access. The abilities to create and delete files, and the ability to change settings within the system. So if you want to change some of the features of Windows, we can stop that with our access rights. Again, it's effective against hackers, the theft of data, and authorized users, but doing unauthorized things. Okay, so making those changes to the operating system. A captcha is where you have to type in some text. It will give you maybe 3 or 4 letters and a couple of numbers, and you have to type in the text into a box. It's very easy for humans to do that, okay, because they can read it and they can see what the text is, even though it may be distorted. However, a computer program or a bot would struggle with that. Okay, you can't do that. So automated hacking programs and bots is very effective against. I've already spoken about automatic software updates. So looking for holes and security vulnerabilities, effective against hackers and effective against viruses and malware designed to attack those holes and those problems with those software. Okay, so the final topic is the ethical, the social, environmental and legal. Okay, I've added 2 more in there, privacy and cultural. Okay, so what are we looking at here? So privacy is talking about how technology affects the privacy of our data and our identity. So it's talking about data theft. is talking about the storage of personal information about us as individuals that potentially could be stolen and then cloned, so we could create a fake identity, okay, based on that data that we could steal. The ethical side is talking about what is morally right and morally wrong. So what do we do in computer science that is morally correct and morally wrong? Okay. The legal is to do with the law. Okay, so what is wrong and right and wrong in the eyes of the law. So what can we do that's breaking the law, basically? Okay. Cultural is talking about how different computer science or different areas of technology can be affected by different ethnic groups, countries or counties, religions, how they affect our use of technology. Okay. And then finally, environmental. This is a big one. Okay. So how does technology and computing affect or impact on the environment? What environmental issues are there that could be created due to our advancements in technology? Okay. So let's just briefly break some of these down. So ethical and legal issues. Okay. You need to be able to define what is meant by ethical. What is right and what is wrong? Okay. Not in the eyes of the law, but just morally. Okay. And then obviously the legal aspect of that as well. Okay. So what does it mean when we say the definition of the legal aspects? Okay. So within the eyes of the law. Some of the issues that they could ask when it comes to questions, okay, could be related to cybersecurity. That is a big, big area within technology at the moment, cybersecurity, okay. That is a very good area because there's lots we can talk about, okay. If I just briefly go back to these slides, this is what we're talking about, cybersecurity. How do we stop viruses, firewalls, authentication into systems, stopping hackers from getting access to our systems, okay? So cybersecurity is a really big topic, and it's worth just looking into that. Obviously, mobile technologies, things like smartphones, are now becoming a lot more common. They are more common. Everyone has one. Okay. How does our reliance on mobile technology come into our lives? Okay. What problems could there be? It could be a social problem. Okay, you could argue that because people use their phones more and more, that actually our ability to socialise and interact in a face-to-face capacity is becoming less and less. We're unable to do that. Okay, wireless networking, so the ability to access our networks from wherever we are. You know, doesn't matter whether we're at home or at work or at school. Having the ability to access that, and what issues does that come with? Okay, it may not be an issue. It may actually be a positive, an advantage. Okay, you should be able to talk about both of these. The rise in cloud storage. More and more systems now utilize cloud storage. Okay, things like Google Drive, OneDrive, Dropbox. They enable us to store our data. Many businesses store all of their information, all of their data in cloud storage systems. Okay, so what are the potential issues with that? Well, we've already looked at that earlier in the live stream, so you should be able to go back to that. The theft of computer code. So if you've made a piece of software, how do you keep that secure? Okay, so that could come down to the idea of proprietary software and open source software. Do you distribute the code with your program? Okay. Is your code freely available on the internet, or is it secured in your network? If the code is able to be stolen, then obviously that is a potential issue there. And then that kind of leads into the copyright. If someone's stealing code, it may be because they want to release a piece of software before you, or an algorithm before you. Okay, so where does the copyright come into that? Okay, if you make a piece of software, do you immediately own the rights to that piece of software and nobody else can copyright it? Okay. Cracking, which is where we take a piece of software and we might crack that piece of software so that we can avoid paying for a security license for it. Okay. Obviously, the cost of software is incredibly expensive. So a copy of Windows can be anywhere up to £250. Some people may come up with a method of actually generating or cracking the license key number so that they don't have to pay for that. Okay, hacking obviously is gaining access to networks. What's some of the issues with that? How can we avoid it or stop it? Wearable technologies, these are things like smartwatches, systems that maybe monitor your steps, your location. Okay, so if you have a smartwatch, it may be constantly monitoring where you're currently located and then linking it with your smartphone and then sending that data back to Google, for example. Okay, so Google has a trace on where you are at all times. And then that can also lead into things like computer-based implants. Okay, so what we mean here is we're actually implanting, so putting in small computer systems inside our body. Okay, we're augmenting our body with computer systems. One example of that could be a monitoring system for diabetics, where a small implant is placed under the surface of the skin and it constantly monitors what your blood glucose level is using that computer. And it can feed that data back via Bluetooth to your smartphone so you can get a very quick and instant update on how your blood sugar level is, so you know whether you need to take more insulin or you need to eat. Okay. And then the issues of data privacy. Okay, what does the government hold about you as a citizen? What rights do you have as a citizen to access that data that is being held by that government? Okay, so these are all ethical and legal issues that could potentially come up on your exam. Environmental issues then, so waste. What happens to old computers when we need to dispose of them? Where do they go? Do they end up on a landfill? What happens to the toxic chemicals and plastics and metals that are stored within them? How do we dispose of them? Do we recycle them in the correct way? Okay, so waste is a big issue when it comes to environmental issues. Okay, and then that follows on to energy. Computers use a lot of energy. They use a lot of electricity. We have to generate that electricity using conventional methods such as power stations. So we may end up burning coal or oil or natural gas. That generates a huge amount of pollution, which, as we know, creates a lot of issues in terms of climate change and the greenhouse gases that are affecting the ozone layer, for example. Okay, warming up the summers and winters, etc. Okay, creates a big problem. Are there environmental issues specifically related to the cloud? Well, yes. All of the data is stored on servers within data centers. These data centers are huge. They hold thousands and thousands of servers that are all using huge amounts of energy, huge amounts of electricity to run. Okay, so there are a lot of potential issues in terms of our growth and our move towards cloud computing, okay, in terms of an environmental issue, but also in terms of our ethical and legal side, okay? And then, of course, resources. Paper. How much paper do we use? Could we reduce our paper use by making use of electronic versions of documents, using things like OneNote, storing them in the cloud, for example? Okay, so if we can have a reduction in the paper that's used, it has a big benefit to the environment as a whole. Okay, image here obviously related to recycling. What can we do? How can we recycle these items so that we're actually making better use of them? Can low spec computers, instead of being thrown away, be repurposed and reused in a slightly different way? Okay. So many things to consider when it comes to the ethics and the environmental issues in terms of computer science, and obviously there's quite a few areas that they can pick from. So I'm going to very quickly go through the Data Protection Act. This comes into the legal side. So the Data Protection Act, there's 8 principles to that Data Protection Act, okay? And it's to do with how we hold your data, okay? So first principle, the data must be secure at all times. That's a pretty obvious one. You must allow the individual to see the data that you're storing about them. So if I've got my address details stored at my local takeaway, they still have to abide by the Data Protection Act. If I want to see what data they store about me, I'm allowed to see that data. I have to request it from them. Okay, the data must be kept up to date. It must be up to date as possible. Okay, the data they store must be relevant. So my takeaway, for example, may store my address details and they may store my credit card details. Both of those things are relevant because they need to know where to deliver my food to, and they also need to know how I'm going to pay for it using my credit card. Okay. However, is it relevant that they store my shoe size? Obviously not. So the data needs to be relevant to what it is they're storing. Okay, and it must be used for the intended purpose. Okay, the purpose of that data being stored obviously is to deliver my takeaway along with my payment. It's the intended purpose. They must obtain that data lawfully. Okay, they cannot steal it. They cannot acquire it from criminal means. I have to provide that data to them, or I have to allow somebody else to give them that data. I have to lawfully let them obtain it. The data has to be accurate. Okay, has to be accurate. They cannot store data that is incorrect or inaccurate, and it cannot be stored for any longer than it's necessary. Okay, in 20 years' time, if my takeaway is still storing my address details, chances are I may have moved, and therefore that data is no longer necessary. So they should not be keeping it for any longer than probably 6 months to a year. Okay, so there's a few different things to think about in terms of the Data Protection Act. Health and safety, this may or may not come up. So this is to do with the health and safety in the workplace regarding IT and computing. So making sure that workstations are not cluttered and congested with paper and boxes and things like that. Providing adjustable tilted screens to make it comfortable for the users. Providing footrests so that they can put their feet up to stop other medical issues. Paying for eye tests for regular IT. So if you're using a computer a lot, okay, your business or your organisation should be paying for eye tests. Providing anti-glare screen filters so that you don't get the light and the glare back off the screen. Adjustable chairs, obviously, so we can make sure we're in a comfortable position. Making sure that the lighting is suitable for the room. That you're not working in dark rooms or overly lit rooms. And obviously allow for regular breaks, okay, to allow some recovery and your eyes to recover. The next piece of legislation, the Computer Misuse Act. This is relating to and was in response to hackers and viruses that were becoming very, very common in the early 90s. Okay, they started to see that there was a potential issue here, a potential problem, so they brought in, certainly in the UK, the Computer Misuse Act. Okay, it's to do with hacking, it's to do with viruses, and there are three main principles. Okay, so accessing computer material without permission, i.e. looking at someone else's files. Okay, if you do that, you are committing an offence under the Computer Misuse Act, because those files do not belong to you and you do not have permission to look at them. Okay. Principle number 2, accessing computer material without permission with intent. So you are going to commit criminal offences. Okay, so you're gaining access to a computer to commit a further offence. So, for example, hacking into a bank's computer and then wanting to increase the amount of money in your account. Okay, so the first crime is the hack that you've done into an unauthorized computer, and then the second crime is you're increasing the amount of money in your account. That's fraud. That's a second criminal offence that you've committed there. Okay, and you've used a computer to do it. And then thirdly, altering computer data without permission. For example, writing a virus to destroy someone else's data, or actually changing the money in an account. So if you actually carry out this hack and you change the money in someone else's account without their permission, you have committed an offence under the Computer Misuse Act. Okay, so three main principles there. And then copyright. If someone illegally uses products from a business, so it's where they download a movie, for example, or a computer game online that they haven't paid for, it's not your property. You need to pay for it. So therefore, if you do that, you are infringing on copyright. And also, if you want to change a product into your own, so you get a piece of software, you copy the design of that software and make your own version of it that has very, very similar features, if not the same features, you are breaking copyright. Okay. Similarly, if you are downloading an image that someone has put onto the internet, maybe it's a photograph that they've taken, and then you edit that image for your own purposes, that is also classed as a copyright infringement. You do not own that picture. You do not have the right to legally change any aspect of that picture. You only have the right to view it on its intended platform, i.e. the internet. Okay, so that is copyright. And I think a few more issues here. So loss of sales could be an issue. Okay, unemployment. So if the business has to go out of business, okay, it can create unemployment. The company will have to pay legal expenses if they want to prosecute you. Okay, so they can lose money, and it may increase prices. Okay, if you are downloading movies and they're losing money, then chances are they want to recoup that money. They may put the price up. Okay, so the people that do actually buy DVDs and buy movies will have to now pay more for them. And then, of course, that might mean fewer products are produced due to smaller budgets. Okay, so less movies are made because they have to cover the costs of where they're losing. Okay, so if a business uses something they've not got permission to use, there could be a loss of confidence. Okay, if you've stolen a piece of software and made your own based on that design, you could lose, and it comes out, you could lose confidence. You definitely could be prosecuted. The brand name is in disrepute, which basically means that your company will be known as a company that steals and tries to pass products off as their own. So your brand or your company name will be wiped off. You could be fined or sued, and you could be forced to withdraw that product from the market, so you can't sell it anymore. Okay, so in conclusion, then there's a lot of topics that we've gone through there. Okay, so make sure we're looking back at data representation, computer systems, so the architectures, the storage, the CPU, the RAM. Networking could be a big topic. Cybersecurity could be in there, as it's a big focus for the government at the moment. And obviously big mark questions on ethics, social, legal, moral, that kind of thing. Okay, so for everyone taking their exam tomorrow, good luck. Remember to read the questions clearly. Make sure you're spacing out your time. Please do not leave any question blank. If you leave a question blank, you've got no marks, so you may as well give it a go. So write something. And thanks for watching. Good luck.